right, team, we finally made it over to question number 4. Okay, so in this one, again, if you need the actual questions, the link is in the description because we're working in the exam book for this one. So question number 4, a unicycle, I can't talk today, sorry, was placed on a stand such that the wheel doesn't touch the ground. We have a crank arm that we apply a force to in order to rotate it. So in part A, there's 2 scenarios. So the first scenario is that the length of the crank arm is L1, speed of the wheel after going through 1 full rotation is omega 1, and scenario 2, the length of the crank arm L2, which is larger than L1, and that angular speed after going through 1 rotation is omega 2. So part A, we wanted to indicate whether omega 2 is greater than, less than, or equal to omega 1, and that is omega 2 is greater than omega 1. So this comes down to, you can actually justify this in 2 different ways. So I'm going to use our text box for this one. So the ways that we can justify this, so we can say that since L2 is greater than L1, the torque in situation 2 is greater than in situation 1. So greater L, greater torque. If the torque is larger, the angular acceleration is larger. If the angular acceleration is larger over the same distance, emphasis on that part, then the change in angular velocity will be greater. So omega 2 greater than omega 1. You could also come at it from an energy perspective. So again, since L2 is greater than L1, the torque is greater. Since the torque is greater, the work done over the same angular displacement is greater. Since the work is greater, the change in rotational kinetic energy is greater. So the angular velocity is greater. And we want to say specifies the angular distance up here. Okay, so you can talk about it in 2 different ways. You can talk about it in terms of the torque, how that affects the acceleration. The acceleration affects the angular velocity over that same distance, that same angular distance, 1 rotation. Or you can talk about it from an energy perspective. So more torque, more work done by that torque, more work done, more energy added to the system, more energy, more speed, or more velocity. Okay. For part B, we want to derive an expression for that angular speed immediately after the crank arm has turned through 1 rotation. So again, we could have done this 2 different ways. We could have done it from the torque angular acceleration perspective, or we could have done it from the energy perspective. And we're going to do both to show you how it works. So if you want to go the torque angular acceleration way, Newton's second law says the sum of the torques is equal to I alpha. The only force applying a torque on our wheel is that applied force at that lever arm, at that length L. So the applied force at L1. And we're rotating the wheel, which they called IW. Unnecessary subscripts, but whatever. And then alpha is our angular acceleration. Okay, so torque, I alpha. Now we need to talk about what alpha is. So since we have a constant torque, a constant angular moment of inertia, goodness, lost my train of thought, our angular acceleration is going to be constant. Which means we can use our constant acceleration equations. So we don't care about time. So we're going to use the time-free one, which is omega final squared equals omega initial squared plus 2a delta x, or theta, since we're talking about angles. We start from rest. We have our omega final. We have our alpha. We go through one full rotation. One full rotation is 2 pi. So my delta theta is going to be 2 pi because that's going to be in radians. So my final angular velocity is going to be 4 pi alpha. So if we sub alpha, that's going to be omega final squared over 4 pi. So we're going to take that and we're going to shove him up in here. So my force times my lever arm is equal to I times alpha, which is omega squared over 4 pi. Okay? And you can keep the little final subscript. I think they called it omega 1 in the actual question, so we're going to call him omega 1, just to be consistent. Okay, so now I'm just going to solve for omega 1. So I'm going to multiply that 4 pi over. So I'm going to get 4 pi force times L1 divided by my moment of inertia. And that's going to be equal to omega 1 squared. So I'm going to square root it to get my final answer. So I get 4 pi force L over moment of inertia. Nice. All right, if you wanted to do it the energy way, then from conservation of energy, or work energy theorem, I guess technically that would be work energy theorem. The work done is going to be the torque times the angular displacement, and that's going to change my rotational kinetic energy. So my torque is the force times that lever arm again. My delta theta is still 1 rotation, so that's still 2 pi. I'm starting from rest, so that change in kinetic energy, and we're grossly ignoring plus and minus signs here, just so we're clear, is 1/2 I omega squared. So if we do the same thing, solve for omega, that gives me 4 pi F L over I, and I forgot the W. W is equal to omega squared, so I can square root it, and I'll get the same thing. So you can do it either way, which is nice. Love that. All right, for part C. So part C says, okay, in a third scenario, now the unicycle is placed on the ground such that the unicycle can move forward without the wheels slipping on the ground. So I'm just going to draw that little situation. So now we're on the ground. We're going to roll without slipping this time. A force of the same magnitude F is exerted at the end of the crank arm of length L1 as in scenario 1. So we still have that weird little crank arm that's getting a force applied to it at some distance L1. And then direction of the force remains perpendicular to the crank arm at all times, which is great, which means that torque is going to be just F times L around this rotation point. The resulting angular speed of the wheel immediately after the crank arm has been turned through 1 rotation is omega 3. How does omega 3 compare to omega 1? So again, there's a couple of ways you can describe this. So if we want to keep our rotation point here, we can talk about it in terms of torque. So the net torque about the center will be less because friction is going to be in the opposite direction. So because friction will provide a torque in the opposite direction. All right, so friction is going to give us a torque in the opposite direction. So the net torque around the center of mass is going to be lower lower net torque means less work. So less torque means less work over one rotation. Less work means less change in kinetic energy rotational. Less k-rot means less angular speed. So omega 3 is going to be less than omega 1. Okay, so that's how we can talk about it in terms of work. You could also try to make the argument in terms of now your rotation point is the ground. So at the ground, friction will not do any work, any torque, because it's being applied at the rotation point. So you could also make the case that the moment of inertia, so the moment of inertia increases because you're not rotating around the center of mass anymore. So because not around center of mass anymore, center of mass, and that's from the whole parallel axis theorem. So if your moment of inertia increases, then your angular acceleration is going to decrease, keeping everything else the same. So larger moment of inertia, or you could actually go this way too. So larger moment of inertia, less kinetic energy, less omega. Because that torque, even though, like, so from that rotation point, that force, it's not going to be a constant torque, first of all, if you measure it around this point, because that R is changing and the orientation of F with that R is going to be changing. So that's going to affect it as well. Yeah, but those are the two biggest ways you can talk about it. You could also make some case about if we also want to talk about energy around this point. So remember, if I'm rolling without slipping, that contact point has a linear speed of 0. My center of mass has a linear speed v, and therefore the top has a linear speed 2v. So you could also talk about it in terms of energy that way. So now that we have the same external force for rotating around this point, that work being done. So work being done is the same from that external force. So work being done is going to be the same from that external force, but now it has to be shared between translational kinetic energy and K rotational kinetic energy. So if you have to put some of that work into getting the center of mass to move, you're going to have less energy going into your K rotational. So you got less K rot, which means less omega, is another way you can think about it. I'm trying to think if there's any other ways, any other things we could say about it. If you said something different, let me know and we'll talk about it in the comments. But yeah, so that's it. I hope you did great. Hope you managed to scrape up some points. If you are a self-studier, or if you just want more help, I am going to be building a bunch of mechanics and E&M resources over the summer. Sign up for my email list below, and I'll be sending you guys some stuff. Okay? Have a great summer, or have a great study time if you're watching this a year from now. We'll see. And yeah, bye!